Next, we're going to consider addressing another fundamental defect in the implementations we've considered so far, that those implementations are only good for strings. What if we want to have queues and stacks of other types of data? And that brings us to the topic of generics. All right, so we implemented stack of strings, but in applications, we have all different types of data that we might want to implement, like a stack of ints, say, or URLs, or cars, or vans, or whatever data that we might be processing. So how are we going to implement stacks and queues for that types of data? Well, the first thing that we might consider, and actually we're forced to consider this one in lots of programming environments, is to implement a separate stack class for each type of data that we're using. That really seems unsatisfactory. We have our carefully crafted code that does array resizing and so forth, and we're going to copy that code and change the data type string to the data type van or int everywhere. And what if we have hundreds of different types of data that we're processing? We're going to have hundreds of different implementations. Unfortunately, that situation at the beginning of Java, we were stuck with that, and there are plenty of programming languages where basically we're stuck with that. So what we want to look at is a modern approach to avoiding having multiple implementations for each type of data. A quick hack that is widely used is to use casting to implement, to reuse the code for different data types. So we make our implementation with type object, so everything in Java is a subtype of object, and then the client, when the client comes to use it, will simply cast the result to the corresponding type. I don't want to spend a lot of time on this because I think this is an unsatisfactory solution. So in this example, we have two types, we have two stacks, one of apples and one of oranges, and then it's up to the client when it pops something off the apple stack to cast it to apple to keep the type checking system happy. The problem with this is that the client code has to do this casting, and it's kind of an insidious bug if it doesn't quite get it. So the third attempt that we're going to talk about uses generics. And that way, the client code doesn't do casting. We can discover mistakes in type mismatches at compile time instead of at runtime. So in this case, we put, with generics, we can have a type parameter on our class, and that's inside angle brackets in this code. And then we can if we have a stack of apples and we try to push an orange onto a stack of apples, then we're going to get a compile time error because that stack was declared to only consist of apples. And just the guiding principle in good modular programming is that we should welcome compile time errors and avoid runtime errors. Because if we can detect an error at compile time, then we can ship our product or deploy our implementation of an API and have some confidence that it's going to work for any client. Whereas if the error is not going to get discovered until runtime, it might occur with some client development years after we have deployed our software and be extremely difficult on everyone. Okay, so actually with a good generic implementation, it's not difficult to simply take every place that we use string and replace it with a generic type name, as in this code here. On the left is our implementation of a stack of strings using linked lists. On the right is a generic implementation. So every place that we use string type on the left, we use the word item on the right. And at the top, in the class declaration, we declare in angle brackets that item is the generic type that we're going to use. The implementation could hardly be more straightforward, and it's an excellent way to solve the problem of handling multiple types of data with one implementation. With arrays, it doesn't quite work, again, all programming languages, or many programming languages nowadays have difficulties with this, and Java's got a particular difficulty. So what we would like to do is just declare a new array using our generic type name item, as in the highlighted line here. Otherwise, it's the same. Unfortunately, Java does not allow generic array creation. So there's various technical reasons for that, and you can read extensive debates about this on the web. That's going to go beyond our scope. For now, what we need to do is put a cast in to make this work. So we create an array of objects, and then we cast it down to an array of items. Now, in my view, good code has 0 casts. So we want to avoid casts as much as possible because it really is declaring some kind of weakness in what we're doing. But in this case, we have to put in this one cast, and so we'll refer to that as the ugly cast. It doesn't make you feel good about the code. It's not something that you'd come up with on your own, and that's an undesirable feature, I think, for code so simple as this. But fortunately, we can get through pretty much everything that we're going to do in this course with just knowing about this one ugly cast. So now when we compile this program, we get a warning message from Java that says that we're using unchecked or unsafe operations, and we should recompile with -xlint equals unchecked for details. So we can go ahead and do that, and it says that you have put in your code an unchecked cast, and we're warning you about that because you shouldn't be putting in unchecked casts. And okay, that's fine, and you're going to see that when you do compiles using code like this. I think maybe they might have added to this warning statement, we apologize for making you do this. It's not our fault that we had to do that. We had to do that because of your requirement about not allowing us to declare generic arrays. So with that note, please don't think there's something wrong with your code if you follow our prescriptive and get this warning message. Okay, there's one other detail that Java takes care of, and that's what about primitive types. The generic type that we're using is for objects, and we're casting down from array of objects. In order to handle generic types, we have to use Java's wrapper object types. Integer with a capital I is wrapper type for int, and so forth. Many of you are probably familiar with that. And there's a process called autoboxing, which automatically casts between primitive types and wrappers. So all of that handles the problem of dealing with primitive types kind of behind the scenes. And the bottom line is that we can articulate an API for generic stacks that works for any type of data, and we've got 2 implementations, linked lists and arrays, that perform very well for any type of data using the resizing or linked lists as we've described.